To calculate the exciting current for a ring with a gap cut in it, use the equation I equals B times L times N divided by micro 0 times A. In this equation, I represents the exciting current in amps, B is the flux density in Teslas, L is the length of the cut in meters, N is the number of turns in the ring. Micro 0 is the permeability of free space, which is 4 times pi times 10 to the power of negative 7 henries per meter, and is the original cross-sectional area of the ring in square meters. It is essential to ensure that all values are in the correct units before substituting them into the equation. If the flux density is given in Gauss, convert it to Teslas. To convert Gauss to Teslas, use the conversion factor 1 Tesla equals 10,000 Gauss. Therefore, divide the value in Gauss by 10,000 to obtain the equivalent value in Teslas. Similarly, ensure that the length of the cut and the cross-sectional area are expressed in meters and square meters respectively. If these values are initially given in other units, such as centimeters or square centimeters, perform the necessary conversions before using them in the formula. The permeability of free space, denoted as micro 0, is a constant value equal to 4 times pi times 10 to the power of negative 7 henries per meter. This value represents the ability of a vacuum to support the formation of a magnetic field. When using the equation, substitute the numerical values for each variable, ensuring that they are expressed in the correct units. Perform the calculations according to the order of operations, first multiplying the values in the numerator, and then multiplying the values in the denominator. Finally, divide the numerator by the denominator to obtain the value of the exciting current in amps. The exciting current is the amount of current required to establish the specified flux density in the ring with the gap. The gap in the ring introduces an air gap into the magnetic circuit, which increases the reluctance of the circuit. Reluctance is the opposition to the flow of magnetic flux, analogous to resistance in an electrical circuit. The presence of the air gap requires a higher exciting current to overcome the increased reluctance and establish the desired flux density. The number of turns in the ring, N, also affects the exciting current. A higher number of turns results in a stronger magnetic field for a given current. Therefore, if the number of turns is increased, the exciting current required to establish the same flux density will decrease. Conversely, if the number of turns is decreased, the exciting current will need to be increased to compensate for the weaker magnetic field. The cross-sectional area of the ring, A, also plays a role in determining the exciting current. A larger cross-sectional area provides a larger pathway for the magnetic flux to flow, which reduces the reluctance of the circuit. As a result, a lower exciting current is required to establish the desired flux density. Conversely, a smaller cross-sectional area increases the reluctance and necessitates a higher exciting current. In summary, the equation I equals B times L times N divided by micro 0 times L allows you to calculate the exciting current required to establish a specific flux density in a ring with a gap cut in it. By ensuring that all values are expressed in the correct units and substituting them into the equation, you can determine the exciting current in amps. The exciting current is influenced by the flux density, the length of the cut, the number of turns, the permeability of free space, and the cross-sectional area of the ring. Remember to consider the impact of the air gap on the reluctance of the magnetic circuit and adjust the exciting current accordingly. The units must be consistent for accurate calculation. Ensure length is in meters, area is in square meters, and flux density is in Teslas. If length is given in millimeters, divide by 1000 to convert to meters. If the area is given in square centimeters, divide by 10,000 to get square meters, since 1 meter is equal to 100 centimeters, so 1 square meter is equal to 100 times 100 square centimeters, which is 10,000 square centimeters. If the flux density is given in Gauss, divide by 10,000 to convert to Teslas. This is because 1 Tesla is equal to 10,000 Gauss. Be sure to use the correct units in the calculation so that the answer will be correct. The permeability of free space is a constant and is 4 times pi times 10 to the power of negative 7 henries per meter. Make sure the number of turns is a dimensionless number. When you have all the variables correct, then you can get the answer of the exciting current in amps. This formula is derived from Ampere's law, which relates the magnetic field intensity around a closed loop to the current flowing through the loop. In this case, the closed loop is the magnetic path within the ring, and the current flowing through the loop is the exciting current. The gap in the ring disrupts the uniformity of the magnetic field, causing fringing effects at the edges of the gap. Fringing effects refer to the spreading of the magnetic flux lines as they cross the air gap. This spreading reduces the effective cross-sectional area of the magnetic path and increases the reluctance of the air gap. The length of the air gap has a significant impact on the exciting current. A longer air gap introduces a higher reluctance, requiring a greater exciting current to establish the desired flux density. The relationship between the air gap length and the exciting current is approximately linear, meaning that doubling the air gap length will approximately double the required exciting current. The material of the ring also influences the exciting current. The permeability of the ring material determines its ability to support the formation of a magnetic field. Materials with higher permeability, such as iron or steel, require lower exciting currents to establish a given flux density compared to materials with low permeability, such as air or plastic. The equation assumes that the magnetic field is uniformly distributed within the ring and that the fringing effects at the air gap are negligible. In reality, the magnetic field distribution may not be perfectly uniform, and fringing effects may be significant, especially for longer air gaps. In such cases, more advanced analytical or numerical techniques may be required to accurately calculate the exciting current. These techniques may involve using finite element analysis software to simulate the magnetic field distribution and account for fringing effects. The temperature of the ring can also affect the exciting current. The permeability of magnetic materials typically decreases with increasing temperature. This decrease in permeability increases the reluctance of the magnetic circuit and requires a higher exciting current to maintain the desired flux density. The equation assumes that the temperature is constant and that the permeability of the ring material is known at that temperature. If the temperature varies significantly, the equation may need to be modified to account for the temperature dependence of the permeability. The frequency of the exciting current can also influence the behavior of the magnetic circuit. At higher frequencies, eddy currents may be induced in the ring material, which can oppose the flow of magnetic flux and increase the effective reluctance of the circuit. Eddy currents are circulating currents that are induced in conductive materials when they are exposed to a changing magnetic field. These currents dissipate energy in the form of heat, which can reduce the efficiency of the magnetic circuit. The equation assumes that the frequency of the exciting current is low enough that eddy current effects are negligible. If the frequency is high, more advanced models may be needed to account for eddy current losses. The shape of the ring can also affect the exciting current. The equation assumes that the ring is a perfect toroid, which is a donut-shaped object with a uniform cross-section. In reality, the ring may have a more complex shape, such as a rectangular or square cross-section. The shape of the ring can affect the distribution of the magnetic field and the reluctance of the magnetic circuit. For non-toroidal rings, more advanced techniques may be needed to accurately calculate the exciting current. The surface finish of the ring can also influence the exciting current. A rough surface finish can increase the effective air gap between the ring and the magnetic core, which can increase the reluctance of the magnetic circuit. The equation assumes that the surface finish is smooth and that the air gap is minimal. If the surface finish is rough, the equation may need to be modified to account for the increased air gap. The presence of any other magnetic materials in the vicinity of the ring can also affect the exciting current. These materials can alter the distribution of the magnetic field and the reluctance of the magnetic circuit. The equation assumes that the ring is isolated and that there are no other magnetic materials nearby. If there are other magnetic materials present, more advanced techniques may be needed to accurately calculate the exciting current. The accuracy of the measuring instruments used to determine the values of the variables in the equation can also affect the accuracy of the calculated exciting current. The equation assumes that the values of the variables are known with perfect accuracy. In reality, there will be some uncertainty in the measured values, which will propagate through the calculation and affect the accuracy of the result. It is important to use accurate measuring instruments and to estimate the uncertainty in the measured values in order to assess the reliability of the calculated exciting current. Remember to always double-check your units and calculations to reduce the chance of error.